Hello everyone, I am Vishal Chudasama from Sony Research India. The title of this presentation is Open Set Object Detection by Aligning Known Class Representations. The open set object detection is aimed to detect new or unidentified objects as unknown class along with detecting known objects. However, existing framework suffers from misclassifying unknown object with high confidence, which is exacerbated when an unknown object is semantically closer to known object. For example, the zebra, which is an unknown class, is misclassified as known class with labeled as horse. Another issue is constant RPN learning, which results in overfitting on the training classes. This research work aims to propose a new OSOD framework which aligns class representations effectively by learning clear class boundaries, especially between semantically closer classes as visualized in Figure 2, and detects the unknown as well as known objects accurately as compared to existing SOTA methods, which can be also visualized in Figure 3. This shows the architectural diagram of the proposed method, which consists of three modules called semantic clustering, class decorrelation, and object focus loss on top of the faster RCNN baseline framework. Now I will give brief details about these modules. First is semantic clustering module, which establishes clear semantic decision boundaries and minimizes the misclassification of unknown object. Here we calculate the cosine similarity between feature embeddings of M sampled proposals and text embeddings from K known classes. Then semantic clustering loss is calculated between cosine similarity scores and one-hot encoding of known classes. Second is class decorrelation, which helps the proposed method to enhance the inter-class distance and creates better separation of known classes. Initially, subset of features have been created by sampling one feature for each distinct class of m number of proposal features. Then to perform orthogonality constraints, we compute cosine similarity and then calculate corresponding correlation for all the sampled features. Finally, class decorrelation loss is computed between correlation scores and identity matrix. Third one is object focus loss, which leverages the concept of centeredness to consider critical attributes like object location, shape, geometric properties to learn objectness. The centeredness loss is calculated between centeredness logits and centeredness targets. Finally, the object focus loss is calculated by geometric mean of centeredness loss and region proposal network based object classification loss. This shows some experimental analysis details. In this research work, we also employ the entropy thresholding evaluation technique to penalize the low confidence outputs. For training and testing purpose, we use Pascal VOC and MS-COCO datasets into open set evaluation settings. We perform evaluation on standard open set metrics as well as closed set metrics. Also introduce a new metric called harmonic mean precision to evaluate performance on known and unknown objects in one metric. This shows quantitative comparison with existing methods on T1 setting. Here the proposed model performs better than other methods except the MAP of known objects for cases having ResNet 50 as backbone. Similar analysis is presented here for T2 setting, where the proposed model outperforms existing method except the MAP for known object metric on classes having ResNet 50 as backbone. This shows comparison on introduced harmonic mean precision metric on T1 and T2 setting. Here the proposed methods perform better than the other methods in all scenarios. This shows visual comparison between proposed and baseline methods, where one can see that the proposed method detects known as well as unknown objects accurately as compared to other methods. These are the references that have been used in this presentation. Thank you.